In this video, we're going to visit a very core fundamental part of the ANOVA analysis, which is the assumptions that we make when we implement the ANOVA and how we check if those assumptions are reasonable. Now, checking assumptions is something that you may or may not have done previously, but it is an extraordinarily important part of implementing any kind of statistical analysis. And really, with almost any analysis that you do make some assumptions, and those need to be checked out. Now, what are some of the assumptions that we make when implementing ANOVA? Well, there's a variety of them. The first is normality. The second is homogeneity of variance. Third is independence. And then we also have this kind of assumption of good model fit. And the book actually talks about what to do if some of these different assumptions are violated. For example, transformations is an option that the textbook talks about. We're not going to focus on that too much in this particular course, but that is there in the textbook if you're interested in checking out some of the details on that. And we do talk about that in much more detail in some other courses. That's just not what we're going to focus on when our focus is primarily on the design piece. So there is a traditional acronym for the different assumptions. It is LINE. It stands for linear, independent, normal, equal variance, LINE, line. Now that's for regression. We don't have a linearity assumption in ANOVA. We just have the INE, independence, normality, and equal variance or homogeneity of variance. So that's something that you can use to try to help you remember if you want to. Now there's a variety of different techniques that we can use to address these, both statistical and graphical. I tend to focus on the graphical methods. They give a lot more information. They tend to be a lot more reliable than the statistical methods are. Students often like the statistical methods because there's a clear, a p less than 0.05 or greater than 0.05. But really, the graphical methods are far superior. So we're going to place heavy emphasis on the graphical methods but because honestly, that's how it tends to be done and is a better use of your time and knowledge. If you want to jot down some of the different statistical methods, you can. For statistics, the tested normality, we can use something called the Kolmogorov-Smirnov or Anderson-Darling or Shapiro-Wilks. For homogeneity of variance, Levine's test or Brown-Forsyth is probably a better option. And then for independence, you can do a Run's test. Now, actually, one interesting thing about independence is, as we'll talk about when we address that particular section, independence comes more from the study design than it does from any other thing. So while normality and homogeneity of variance have to do a lot with the data, and we don't really know ahead of time, independence, if we design the study right, is not a concern. So independent, we look at how is the study designed, and then we can make a claim about independence. As far as plots that we'll talk about, normality, we'll talk about checking with a QQ plot or the PP plot. Homogeneity variance, we'll talk about checking with a residual versus predicted plot or a box plot, residual box plot. And then independence, we'll talk about with a time plot. So for more detail on the statistical tests, feel free to check different courses. An ANOVA course would have more detail on that, or non-parametric statistics would actually show you how to construct some of these statistical tests, because some of these are non-parametric statistical tests. And those also we'll talk a little bit more about how to fix these. In practice, I should mention, I suppose before we move on, that in practice I do use both. But really I only interpret the plots. I like glance at the statistical test, but if there's any disagreement between a plot and statistical test, I always go with the plot, not the statistical test. So I really only look at the plots. All right, well, now that we're talking about assumptions, something happens to our order of operations. And with the order of operations, what happens is that assumptions come first. So whenever you're doing an analysis, the very first thing you do as part of the analysis process, like you can do descriptive statistics, that's fine. You can do some some basic plots of data, that's fine. But before you look at any ANOVA, anything with a p-value, anything with a distribution, any test statistics, any of that, before you look at any of that, you look at assumptions. Assumptions come first. And this is going to be true for all of your statistical analyses from now on. Once you know about statistical assumptions, it's going to be expected that you check statistical assumptions before you do an analysis. So now if you do an ANOVA for my class, you should check the statistical assumptions and make sure they pass. And then you can turn in your results. Or then you can go on to interpret the results. And if they don't pass, then you don't move on till interpretations until those assumptions are fixed. So you're kind of stuck. Now I want to pause here and say, again, though it's not a huge focus in our class, there's some really easy things to do if they don't pass. So like if normality doesn't pass, we use a non-parametric ANOVA. And as long as you know the name of it, it's really easy to implement in a software like R, and you just drop it in and it works great, and you don't really have to worry about it. So it's not particularly complicated if the assumption doesn't pass. Just have to make a slight change. Sometimes it can be a little more complicated. But of course, often with things like normality, it's not particularly complicated to fix. The trick is that you have to fix it. So don't move on till interpretation until they're fixed. This said, most situations are pretty gray. So it's not that it's broken or it's not broken. It's kind of like a meh deal. And so what we're looking for is not, is it possibly broken? Are the assumptions possibly broken? What we're looking for is really strong evidence that, yeah, that assumption is pretty violated. Like that data is not even close to normally distributed, or the variances are not even close to being the same. So that's the kind of thing we're looking for, is not just weak evidence, but really strong evidence. So if it's close, then we're not going to worry about it. But if there's really strong evidence where you kind of like sit back and you're like, wow, I didn't even know data could get that non-normally distributed, then that would be a case where you may have a violation of an assumption. And again, if that happens, then you don't move on to the analysis and interpretation until you fix that violation. So if you have really bad violations, you need to pause and fix them. Now, one of the nice things is that ANOVA, especially if you have a balanced design, that means you have an equal number of replications within each of the factor levels. If you have that, that's called a balanced design, then ANOVA is pretty good about violations. So if you have, if your data aren't normal, even if they're like pretty not normal, then it doesn't really impact ANOVA, and that term is called robust. So when a violation of an assumption happens and it doesn't really impact the validity of the analysis, then that analysis is called robust to that particular violation. So when the sample size is equal, ANOVA tends to be pretty robust to normality and homogeneity of variance. When the sample sizes within the groups aren't equal, then it's not quite that straightforward. It might be a bigger issue and is worth taking a little more time to look into. Now, with ANOVA specifically, we want to be careful if it gets to be a stronger thing. So again, it's not invincible, though it is robust. You can't have these massive violations of these assumptions and expect it to work out well. What you can say is that if it's even a moderate violation, it tends to be okay and we can still move on. But if it's a massive violation of one of these assumptions, then you're really going to need to stop, and you can't move on until you fix the assumption. So how do we tell if it's a massive assumption? I know I'm kind of putting the cart ahead of the horse here a little bit, but how do we even check the assumptions in the first place? And we're going to have some different strategies depending on the assumption that we're checking. So let's start with the normality assumption. And actually, let's start even a bit ahead of the normality assumption and talk about what we mean by assumptions. Well, in assumptions, when we talk about assumptions, what we're talking about is the assumptions that we make on the error terms. Now, you'll see this term residual thrown out, and again, you can check the textbook if you want to. But the term residual just means an observed error. So we had the Greek letter epsilon for the theoretical errors in the population, but just like we have observed group means to represent our mu's, we have observed errors, E, to represent our epsilons. So this is the observed error in the data. So it's the difference between the observed data and the predicted data, or in ANOVA, the difference between the observed data and its group mean. This is the error term. And actually, you already saw this. This was part of the sums of squares of error. And this is what we call a residual. It is an observed error term, is the best way to think about this. So the assumptions that we have come from the distribution of the residuals. We said epsilon, and I'll try to draw this out real quick just to remind you. We have epsilon was distributed as a normal with a mean of 0 and a standard deviation of sigma squared. And actually, this contains all of our assumptions. A mean of 0, epsilons are all distributed the same way with a constant error term, sigma squared. There is no subscript on the sigma squared. What does that mean? That means all of the errors are distributed the same variance, homogeneity of variance, equal variance. All of them have the same variance. That's where that comes from. And then all of the errors are distributed independently, so they all follow this distribution. So that's where these assumptions are coming from, is this distribution of the error terms. So to check the assumptions, we check the observed errors, which are called the residuals. Now, computer software can generate these residuals, so you don't have to look at them by hand. There are different plots that we can use. Residual plots are very helpful, and we'll talk about them on the next slide. But one that's really helpful in normality is something called a normal probability plot, and something called a QQ plot fills a similar role. So probability plot, PP plot, QQ plot, these are very similar analytic tools that we can use to look at residuals. All right, so let's look at some good examples and bad examples. Let's first look at a pretty decent example. So what ends up happening in a QQ or a PP plot is we have this positive sloped line and then data kind of strewn about it. Now, in a good example, the data points fall pretty close to the line. So this is an example of a good PP plot or a good QQ plot. And actually on the next slide, I'll probably very poorly draw out some examples. Now, so I mentioned previously, but I guess I made a note here too, that statistically, one of the methods that we use to test this is the Shapiro-Wilks normality test. But again, graphs tend to be preferred, and sometimes students ask why. The thing with graphs is twofold. First of all, depending on the problem, that can inform you as to what the solution should be. A Shapiro-Wilks test, if I ran that, I'd get a p-value greater than 0.05, which would indicate no violation, or a p-value less than 0.05, which would indicate a violation. By the way, that's an important thing when we're testing assumptions. When we're testing assumptions, the assumption is okay if the p-value is greater than 0.05. I'll say that one more time. When we're doing a statistical test of assumptions, everything is good. We don't have to worry about anything if p is bigger than 0.05. So normally when we're doing an analysis, we want p to be less than 0.05. But in assumptions, we want p to be bigger than 0.05. So that's kind of an opposite thing. If p is less than 0.05, that means we have a statistically significant problem. And we don't want significant problems. We want not significant problems, which is why we want p to be greater than 0.05. But if p is less than 0.05 for a test, then we have a problem. So that's something to write down on your notes, put a little star next to. It's kind of an important thing, especially if you plan to use any statistical tests for assumptions. Now, let's draw out a couple of normality examples, the PP plot and QQ plot examples. So first of all, we had the good one. The good one had our different data points kind of strewn about, and you're not going to see them randomly strewn about like this. They're actually going to be much more linear, and they're kind of around this line that goes up and over. Another one that we can have is we could have something like where we have a kind of this kind of goes up and over like that, where we have almost a cubic shape on the line. So that would be a bad example. And then another bad example would be what we call a lazy S. So if you think about kind of this S goes over and across, that would also be a really, really bad example. So these bottom two are the things that you'll pretty often see. I mean, sometimes you see things, that's another bad example. So something like this would be a bad example, or the opposite of that, where we have it kind of go up and over. That would be a bad example. All of these are bad examples. What you're really looking for, again, as far as something good, is that all of these dots are right on the line or really, really close to the line. Now, what happens if you have something like this in the bottom left, where we have it being pretty close to the line, but maybe it kind of goes a little up and a little over, but it's still pretty close? Well, that's kind of a shade of gray, and really it's experience that helps you figure out when that's a problem or when that's not a problem. And we'll have in our R section, we'll talk a little bit about how we can practice getting a feel for that and what we can do there. As far as getting you used to, as fast as possible, getting you used to figuring out, is this bad enough to be a problem? But typically, if it's pretty close to the line, I'm not worried about it. What I'm really looking for, again, even moderate violations aren't too big in ANOVA. What I'm really looking for is these much more extreme violations. Now, another thing that happens when you're looking at these in an ANOVA is that sometimes the different values will be, actually that's not the example I wanted to do, I apologize. Sometimes the different values will be a little bit more linear, and that's okay. So you may have little chunks of points that are kind of together in different areas with the line through them. So you're still looking for, do they fall reasonably close to the line, even if they come in little chunks like that. All right, independence and homogeneity of variance in ANOVA. So for independence, we are really looking at let's start with the classic case of not independence. A classic case of not independence is I have twins in my study, or I have a husband and wife team, or brother and sister, or something that relates different aspects of my sample in a way that I'm not accounting for. That is a classic violation of independence. Sometimes run order can be an issue, where the order in which things were run, if I start doing squats and then I have to do squats like 10 runs in a row, well, I'm going to take a lot longer to do squats on the 10th run than I am on the first run. So run order may be a violation of independence. But in general, independence is any relationship among the data that we're not accounting for in the model. Now we can, like for run order, if I know the order that the data were run in, and you don't always know this, put a big star next to that statement. You do not always know the run order. If you create the design, you do, if you tracked it. But if you're just looking at a data set, you don't always know this. But if you do have the run order, then you can plot the data over the run order and see, is it pretty randomly spread? That would be a good thing, because we don't want run order to be a factor. We don't want it to be related. Now, if I were doing squats, then what you might see is, well, starts by doing them really fast and then gets slower over time. That would be a bad thing, where I see a pattern in that run order graph. So independence, what we're trying to say is that there's no unaccounted for patterns in the data. And again, typically that's done by design. Well, I don't put twins in my data set without accounting for that. I don't put a husband and wife team in my data set without accounting for that. I don't put a brother and sister in my data set without accounting for that. So independence on the first slide when we talked about it is often done by design, and that's what we mean. Now for homogeneity of variance, to check that, we can plot residuals versus the predicted or fitted values. So as the different predictions happen, we look at each of the predicted values and see, are the residuals, homogeneity variance means, are they spread about evenly? So in this case, the spread in each of these 4 sets of predicted values is relatively even. Now, recall that the predicted values, well, that's just our group means. So actually the way in which we do a plot of residuals versus fitted values in ANOVA is often just using a regular old box plot. And we look at the width of the boxes. For homogeneity of variance, we want the boxes to have relatively similar widths, but between all of the different groups. So this type of a plot is actually really useful for a wide variety of different situations. It's not just in ANOVA, like in regression, these plots are really useful in a whole bunch of different types of analysis in terms of checking in with the homogeneity of variance or heteroscedasticity assumption. That's the regression one. Again, when the sample sizes are relatively equal, this isn't as big of a deal. So for the homogeneity variance, the statistical test is that Brown-Forsyth test for the independence of run order. And again, that's not independence of everything. That's just independence from one order. You still could add twins in the run order, but you can test that through a correlation between run order and the residuals. But let's draw out a couple examples for the homogeneity variance of these different boxes if I can. And actually what I'll just do is I'll draw lines instead of boxes. So these vertical lines are going to represent my box plots because I'm not fancy enough to represent box plots. But if I have something like this, this is not going to represent a problem because all of these different pseudo box plots here are relatively the same width. This last one's a little bit smaller, but it's not the location that's important. It's not the location that's important. So this one's actually okay. The important thing is the width of the boxes. So let's say I had something like this. That's one box, that's another box. And then maybe I have one that's kind of in the middle. So this is where we're going to see a problem because you see that the width of this first box and the width of this second box are way different, and that's what's going to create an issue. So how do I know when it's a real issue? Well, honestly, again, this is a kind of a tough thing to interpret, and it really depends on the context. It depends on the sample size. If this were a balanced sample size, this might not be that big of an issue overall. If it were an unbalanced design, then this does become a lot more problematic statistically because some of our assumptions are based on the fact that these have the same variance, and if that isn't true, then that violates our assumption and it violates the validity of our statistical test. All that means is that when I make a conclusion of statistically significant or not statistically significant, that's no longer supported. If the validity of the test is in question, then the claims about significance are no longer supported by the data, and that's a problem. So, this bottom case is a pretty extreme one, but maybe something that's a little bit less extreme that might actually happen is something like this, where you see that this top left one and the middle one, or even the top right one, I mean, this middle one definitely looks like it's got a smaller width than that top left one. But how do I know if that's small enough? And the general rule of thumb is if you have a balanced design, you can be pretty flexible. So in this particular case, this would actually be just fine if we had a balanced design, probably. But over here on the left, even with a balanced design, this might be concerning. Actually, with a balanced design, this might even be okay. But if you have these massive, massive, massive differences between the variations, that's when you want to pause, really take a look. I'd call this pretty minor difference. This would be moderate, moderate on the heavy end of moderate, maybe going to a little more extreme. And then, of course, if you got way, way, way extreme, that's a case where you're going to want to pause and really make sure you fix that assumption before you continue on. So this has been a presentation of the different assumptions that we have in ANOVA. In the next video, we're going to jump into the post-hoc comparisons, really talking about how do we, after the ANOVA, figure out where those differences lie in the group means.